So you'll still do the normal CDF, but you'll put in a lower bound and upper bound and the actual mean and standard deviation. So let's try it. If the SAT scores are approximately normal with a mean of 1026 and a standard deviation of 209. So that means mean equals 1026, standard deviation equals 209. What proportion of students have scores greater than or equal to 820? So we're looking for the probability that X is greater than or equal to 820. I always draw a picture. Your picture should be centered at the mean. Here's 1026. So 820 should be over here. If I'm looking for the area to the right, that should be a pretty big area, bigger than 0.5. And that kind of helps me kind of double check my work and like, should this be a big area, a small area? Okay, so we're just going to put it in our calculator. We use the normal CDF. Okay. We'll do our lower of 820, our upper of like a billion or something really, 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 really big. And here are our mean and standard deviations. Okay, so my lower bound again was 820. My upper bound is some ridiculously big number. It's supposed to go to infinity, but we can do a really big number instead. Our mean is 1026 and our standard deviation is 209. And this gives me 0.8378. So about 83% of students have a score greater than 820. Now, you've never done it the old way, but just trust me when I say this is so much faster than doing it the old way. Let's try another one. Automaker A claims that the mileages of all of its mid-sized cars are normally distributed with a mean of mu equals 33 and a standard deviation of 0.7. Assume their claim is true. Calculate the probability the mileage of a randomly selected car is between 32 and 35 miles per gallon. So first, write down for yourself, mu equals 33, sigma equals 0.7, and we're going to want to use a normal CDF function. Let's see, I'll draw my picture. We should be centered at our mean of 33. It looks like I'm looking for the probability that X is between 32 and 35. So here's my 32, here's my 35. We're looking for this area in between. So I'll go to my calculator. I'll do a normal CDF. My lower bound is 32. My upper bound is 35. My mean is now 33, and my standard deviation is 0.7. So it looks like we're at 0.92129. So about 92.129% of the cars will have mileage between 32 and 35 miles per gallon. Let's assume their claim is true. What's the probability of having a car with a gas mileage of 31.2 or less? Okay, so we'll draw our same picture. 31.2 should be about here. We're looking for the area to the left. That should be a smaller area. Okay. So we'll do 31.2 as my upper bound and negative some really big number for our lower bound. We're looking for the probability that X is less than 31.2. Make sure you use the normal CDF. My lower bound now is this negative, really big number. My upper bound is 31.2. My mean and standard deviation are still the same. And notice it gave me 0. This is why you should always double check your work. Notice I didn't put in 31.2. I accidentally did 3.2, so let's fix that. So this is a TI-84 emulator. I've actually never really used the TI-84 before, but I did notice here when I put in too many zeros, it gave me on my negative like 1 trillion or whatever that is for my bottom lower bound, it gave me 0, and I knew that wasn't right. If I cut off a few of my zeros and only did to about 1 billion, then it gave me an answer that actually is right. I'm not sure if that's the emulator or the actual TI-84. So I guess as you try this on your own, put it in. If you get a 0, then you'll know that you're putting in too many zeros. Try it again and make sure you're getting the same correct answer. I'm guessing this is just a flaw in the emulator. I'm not quite sure. So just notice if you're getting a 0, go back through. Maybe you shouldn't put in quite as many zeros. Okay, but we did find this probability, so there's only about a 0.5% chance that someone is going to get a mileage of less than 31.2. Now, a testing agency goes ahead and randomly selects a car from automaker A and finds that it has a gas mileage of 31.2. And we're wondering, do you think that automaker A is telling the truth? Okay. So remember, automaker A said that their mileage is 33 and a standard deviation of 0.7. But we did find a gas mileage of 31.2. So let's see. So if the automaker is telling the truth, and that big part here is the if is if they're telling the truth. Okay. So if they're telling the truth, and the mean is 33 and standard deviation is 0.7, then there is only a 0.5% chance of getting a car with mileage 31.2 or less. Okay. But we did find a car with mileage 31.2. Okay. So they said the average should be 33. And that means the probability of getting one all the way down at 31.2 is only a 0.5% chance. But we did find one that low. So to me, since I know I found one that low, this makes me think maybe their mean of 33 is off. So maybe whatever made them say mean of 33 was wrong, because I shouldn't have actually gotten a car with a mileage as low as I did. Or at least the chance of getting a car with a mileage as low as I did is very small at only 0.5%. Okay. There's a couple for you to try, and then we can go in the other direction. So what if we know the probabilities and we want to find the x values? So we can use our calculators again, but most calculators will want the area to the left. The TI-84 does make you have the area to the left. The Casio actually lets you choose. So if you have that one, some of these will be a little bit easier for you. So let's start with just a z-score. Remember, z is standard normal. Which means that mu equals 0 and standard deviation equals 1. So in this case, we want 20% of the area to the right. So that means it's like we're trying to divide our curve and have 20% of the area to the right. And we want to find this z value that does that. Okay. So 20% to the right. But my table or my calculator only lets me do areas to the left. So you have to use the complement rule here. So if there's 0.20 to the right, then that means there's 1 minus 0.2 or 0.8 to the left. So I'm going to use my calculator. Notice now we switch to an INV norm. That stands for inverse normal function. So we need to use the inverse normal function. It automatically does areas to the right, or sorry, to the left. So I'm going to do with my area equals 0.8. And again, my mean equals 0, standard deviation equals 1. So second distribution again, we want to do an inverse normal. My area is 0.8. My mean is 0, standard deviation is 1. Oh, never mind. Apparently, when I read the manual was wrong. You may or may not have a calculator that makes you do it to the left. So let's do tail equals left and see what I get. So the area to the left is 0.8, sorry, got distracted. So z equals 0.8416. That's the z value that splits it into left and right. So z equals 0.8416. Apparently, this calculator has been updated and I can choose between left and right. So I could go back to my inverse normal. I could do 0.2 to the right, keep everything else the same and change to the right tail. And notice I still get the same z value. So it just depends on what calculator you're doing, whether or not you have to learn these tricks, or you can just put it straight in. So in this next example, let's find a z-score that has a combined probability of 0.1 in both tails. So we want the same amount in each tail, but we want a total combined probability of 0.1. So that means if we divide it by 2, that's going to be 0.05 in each tail. So we have 0.05, 0.05. And we want to find the z-value that does that. Now again, this is going to be our standard normal because it's a z, with mu equals 0 and standard deviation equals 1. There's 3 different ways I can put this in my calculator, so let's kind of see how tricky we can be. So we want our inverse normal. If I want to do left, then my area would be this 0.05. So let's put in an area of 0.05. And do left. And it tells me this z value is negative 1.645. Okay. What if I wanted to look up this z value by saying there was 0.05 in the right? I could do a right with area equals 0.05. Oh, let's see. So when I did this, I got z equals negative 1.645. If I put in 0.05 to the right, I get z equals 1.645. So this is positive 1.645. Now when I got the negative over here, I could have just used symmetry to say I know this positive one is 1.645. Okay. So symmetry is very useful. I could also do the center. So if my tails are at 0.1, then that means the middle has to be 0.9. So let's see if I could just try 0.9 in the middle. Let's do 0.9. Let's do center. Okay. And to get 0.9 in the center, you're going from z equals negative 1.65 to 1.65. So it tells you, and again, that we're from negative 1.65 to 1.645. So again, it's nice that this version lets you find either left, right, or middle. Okay. Some of the versions won't, and so you'll have to kind of use these tricks to find it. Let's see, our next example, extensive testing indicates the lifetime of an Everlast battery is normally distributed with a mean of 60, standard deviation of 6. So mu equals 60, sigma equals 6. The manufacturer has decided to offer a free replacement battery to any purchaser whose battery doesn't last as long as it should. How can the manufacturer establish the guarantee period so they only have to replace 1% of their batteries? So it's saying we want to figure out what's the bottom 1%. So 0.01 for the bottom. And we want to figure out which x value this is that splits it into 1% in the bottom. So again, let's do inverse norm. And we'll use an area of 0.01, and it's going to tell me that x is, let's see, so my area is 0.01. My mean now, though, is 60 because it's not a standard normal distribution anymore. My standard deviation is 6, and I want the left tail. So x equals 46.04. So they can replace batteries that last less than 46.04 months. And that will be just 1% of batteries. See another one. Scores on the SAT verbal test in recent years follow approximately the normal distribution. That means we can do our normal curve. With a mean of 505, so mean equals 505, standard deviation equals 110. How high does a student have to score to be in the top 10%? So it's telling us this is 10% or 0.10. And we want to find the score value that divides you into that top 10%. So again, we're going to use our inverse normal function. Okay. And you can either do a left area or a right area. If you do a right, our area equals 0.10. If you want to do a left, if you have 0.10 to the right, then that would be 1 minus that, or 0.9 to the left. So just depending on which calculator you have, you can do a left or right area. So second distribution, we want our inverse normal. Our area, I'm going to do the right here, so area is 0.1. Make sure you use the mean of 505, the standard deviation of 110. I'm doing the right tail. And so x is 645.97. So to be in the top 10%, you need to score above 645.97.